She's like, hello, Mr. Stradalite. From Adelaide. No,
Yeah.
she doesn't talk to rocks. I climb the big rocks. She analyzes them. I don't know, have you climbed any of the big rocks?
I'm not much of a climber. The tallest I've gotten was Lincoln Peak, which is not a big climb. So,
not a big climb, but it's a great view.
Yeah.
Yeah. So she has a master's degree in geology from Brigham Young, and she moved here in 2008 to take an internship position with the park. She was involved in educating a lot of employees and a lot of visitors about nature things in the park, including geology. And now she is serving as executive assistant to the superintendent. Yeah, so she's up in the admin echelon. Her cat's name is Josephine. Very cute cat. I've seen the cat on Facebook. And of interesting note, she did her first 5K on Saturday.
yeah. Thank you. I walked it, so it was good.
You walked it. It's 5K. It's outside.
Yeah.
It's exercise. Last but not least, Nancy, you left your wallet out front. Where's Nancy? Okay, I'll bring it to you. Let's welcome Tegan Tomlin.
All right. Okay, I think I'm on. Let's see. Can you hear me? All right. I'm going to move around a bit. I'll hold some things up. I asked him to leave some of the lights on, so hopefully you'll be able to see the slides and some things. But afterwards, feel free to come up and check things out. Just to get a feel, how many of you are geologists, have studied geology? All right. So I've got a couple publications you may be interested if you want to get really into the nitty-gritty chemistry of some things over here. How many of you have ever taken a geology class, like in college, high school, elementary school? Did you remember learning about the rock cycle? Anybody? Some of you? Yeah. All right, let me quiz you a little bit. How many of you know the 3 basic categories of rocks? We were going to classify them. Okay, yell them out. What's one? Igneous? Sedimentary? Metamorphic. Okay, so when you hear, we're going to talk about some of these tonight. There's a couple that we have examples of those in the park. I won't go through a huge amount of detail on each of those. We'll spend a lot of time going over a lot of different parts of the story of how Glacier came to look the way it is today. And my goal is not to drown you in facts, but to give you a structure to pin things to. How many of you have ever been to Glacier National Park? Raise your hand. Okay, good. I won't make you raise your hand if you have not, but there's always more to learn. And so as you go into the park your next visit, I'm hoping that by giving you some tools to remember, you'll be able to see things around you maybe in a different light, or put that story together in a chronology. And so that's my goal tonight. There's going to be 4 key words I need you to memorize. Okay, I think you can do it. The first word is silt. What is it? Silt. Okay, tilt. Tilt. Slide. Slide. And glide. Slide. Okay, what are they? Tilt, tilt, slide, glide. Okay, so that's how I'm going to break up the geologic story, and we'll talk about each of those categories. I'm way overlooking a lot of things, really cool things, and so I wanted to show a couple of resources in case you wanted to dive in a little bit more. First, have you heard of the Glacier National Park Conservancy? All right, have you ever bought a book from them? Mm-hmm. If not, I recommend one. This is the roadside guide. If anybody worked at the park in the past? All right. If you worked in the park maybe in the 90s or the 80s, you might have seen a larger version of this. A few years ago, I helped out with the Conservancy to do some updates on this, make it smaller so it would fit in your backpack. And my favorite part of this is the fold-out map. So as you're driving the Going to the Sun Road, you can see what layers you're in, and that can help you keep that story going as you're journeying to places like Logan Pass. Now, there's more than the silt, tilt, slide, and glide. There's some really cool geology that we have that most people don't see as they interact with the park in a normal visit. These are things that you would see more on a river corridor and more difficult to get to locations. And so a lot of those tell the story of Glacier National Park area around 40 to 50 million years ago. And that's when you're going to learn a lot about mammal fossils, a lot of insects, all kinds of vegetation, a very different story. It's a little piece, but I'm not going to go into that too much tonight because I want to focus on the majority of the rocks that you're going to see on a normal visit through. But if you want to dive in and learn about some really phenomenal fossils that we have in the park, I would recommend, I can send you, there's a lot of publications on them. One about an ancient rhino, some teeth that they have found. And then this one I would recommend, this is Dale Greenwalt, sorry. He works at the Smithsonian, has done research on some of the insects that they have found in some of these younger sediments. And a chapter of this book talks about some of these blood-engorged mosquitoes and soft-bodied insects that survived through time as fossils. So if you want to dive into those, this would be a book to do that. And then another resource, how many of you have this one at home? Yeah, it's a common resource people have. And this is nice if you want to get that view outside of the park. So a lot of different things. And then here I have two publications. I like this overview that's done by a research group or a couple researchers from the Montana Bureau of Mines and Geology, along with some other groups that put together kind of a summary of park research, or just on not just the park, it includes outside of the park, but the age of our oldest rocks. Okay. And does anybody know how old our oldest rocks are? Yeah. A little younger than 2.5. About 1.5 billion. And so we're going to talk about some of the timelines on that. So this goes into that age period called the Precambrian. And then I also have one that is newer. This just came out in 2024. And this one talks about research being done on trying to find the origin of the sediments that became the rocks of this Precambrian, of these Precambrian units. So this is really technical, but if anybody's like, oh yeah, I want to read that tonight, this is it. So I brought a couple of those. You can grab that and have sweet dreams of lead, uranium, zircon dating. So with that, we've talked a lot. Let's go back. What's our 4 words? Okay. Tonight I like to call this If Rocks Could Talk, which is silly because they do. You just have to learn how to listen. How many of you have been or have seen this view before? Okay, where is this?
Wild Goose Island.
You're seeing Wild Goose Island, St. Mary Lake on the east side of the park. Does this tell you anything geologically? Anything scream something to you?
Glaciers.
Glaciers. What is it about this that screams glaciers? So you're seeing that U-shaped valley. So already from a distance, the rocks are talking. When we get closer and we start looking into those individual layers, they're going to tell additional stories about the past. Now, one thing I want you to keep in mind, an important tenet, is that we often want to understand, if we want to understand the past, there's a saying in geology that the present is what? The present is the blank to the past. Window's a good one, not window. Key. The present is the key to the past. So it's an assumption that if we study how processes work today, then maybe that'll help us understand the past. If I look at a river and how it flows and the sediment that it leaves behind or cuts away, that will help me understand what I'm seeing in the rocks from the past. So there's some things that we're going to see in the rocks that'll give us indicators that we can put together a story. And science is a storytelling. So I'm going to represent one story to talk about what happened to lead to Glacier National Park's appearance. Now, part of that is we need to go back in time. We're going to go back 1.5 billion years. And how many of you have ever heard of geologic time periods? A lot of you. Did you memorize a mnemonic device in school? Cold oysters seldom develop many precious pearls. Their juices congeal too quickly. Except that doesn't work anymore because the tertiary, now we're talking about the Paleogene and the Neogene, so we need to update that. But we've got the Cambrian, Ordovician, Silurian, Devonian. We're going up through time, and it's helping us understand, we break this apart to understand the fossil record. That's giving us this picture, these fossils. If I can find a fossil, an in situ fossil, that means it's an organism that died where it lived. It's going to give me a lot of information. For example, when I was 9 years old, I remember I grew up in Santa Cruz Mountains in California, and my dad took us to these sand hills that were in between where we lived in the Redwoods and the ocean in Santa Cruz. And I remember I was already very interested in rocks. I spent a lot of time in the backyard breaking pieces of gravel open with a hammer. Because I am the 5th of 5 kids, I was basically unsupervised. And so I did a lot of that, and I learned about sparks that happen when you hit gravel with a hammer. But I was always looking at rocks, especially things that sparkle. And I remember being on this sand hill, and there were some college-age kids that had a wooden frame that was on kind of another piece of wood, 2 pieces of wood that propped it up. And they were shoveling sand in, and they were shaking it. What were they doing? They were sifting. They were sifting the sand. What do you think they were looking for? Gold, panning for gold. They're looking for fossils, something that was in the sand. And I have this very strong memory that when I saw them, I also noticed under my feet, there was a rock that looked like a lima bean. And this is the rock. So I still have it all these years later. Can you see what it looks like here? It was sticking up just out of the sand, and I pulled it out. And just like Excalibur from the stone, what did I get? It's a tooth. Maybe a shark's tooth. So this blew my mind as an 8-year-old. Like, what? We're like 20 minutes from the ocean. What does this tell me? If this is from an organism that died where I was, what can I infer about that environment just from this? There was water. The water used to be there. That's one way. That's one idea. What else might you know if you knew that there was a shark? You had sand. There was a sandy environment. It had to have something to eat. You have a whole system that's there along with it. If I really dug in, maybe I could identify the species of shark. I might understand what depth it maybe lived at. And I can start putting together a story of that environment just from one fossil. If you look at this, if we think of our fossil record, one problem we have when we get to rocks that are as old as the majority of rocks in Glacier National Park is that we get to the bottom of this chart. You'll see that the red at the bottom is Cambrian, about 540 million years ago. That's when the Cambrian started. Cambrian, explosion of life. We're really seeing life taking off there. But what's before the Cambrian? The Precambrian, before the explosion of life. And that's going to go down for nearly 88% of Earth's history is the Precambrian. Can we fathom that? When we look at Glacier National Park and the rocks that are there exposed, we're getting this rare glimpse at this incredible resource that tells us about this time long ago. We don't get certain kinds of rocks and fossils often from the Precambrian because some of those rocks are doomed to transform into other kinds of rocks. So think of a sedimentary rock. What happens if you put that under heat or pressure, or heat and pressure? You're going to metamorphose it. What if you put it under so much pressure and heat that it melts? Becomes what kind of rock eventually? An igneous rock. And so what we need are fossils or sedimentary structures that can tell us information about the environment. And we have a huge, incredible section of continuous Precambrian sediments that do that. It's world-renowned. We have designations because of it as being a unique and important place to learn about this interesting window of time. So let's look at some of that. To get it all into our framework, silt, tilt, slide, and glide, again, these are just easy words to remember. They're going to represent other things as well. So silt, I want you to think about deposits. We're building the sediments up. The dates, that's going to be the number one thing you're probably going to see vary from paper to paper, from book to book. That's changed quite a bit. We're dealing with very old dates, and as new research happens, they're getting better technology to refine those dates more. I generally will say about 1.5 billion years ago, but this can range quite a bit. You might see it go up to 1.48, down to 1.34, so that it wiggle room a bit. But we're going to mostly refer to it about 1.5 billion years ago. So as you're reading other older resources, just keep that in mind. You might see some things that go back to 1.6 billion as an estimate, all the way up to 800 million years ago, being the time when we're depositing and this environment is there that we call the Belt Sea. Tilt, we're going to talk about mountain building. That's going to be about 150 million years ago. Think dinosaur times. Okay. And that continues on. We're going to see tectonics, plate tectonics. Did you get chills? I love plate tectonics. So slide. That's where we're going to talk about a little bit of some of the impacts of that plate tectonics. And we'll be talking about it again towards the end of the dinosaur time, 70 to 60 million years ago. And then the last phase we're going to look into is glide, glaciation. Two different periods of that. So we're going to talk about the Pleistocene Ice Age glaciers, the main movers and sculptors of the park, and then our modern day glaciers that are polishing the surface today. So silt, tilt, slide, and glide. These are generic times. And again, you'll see some variation in these as you're going to different resources. That's what I'm going to work with today. Again, if we're looking at geologic time, if we're going to start with silt, we put that time of Earth's history into a round. You have the oldest is, oh no, I don't know where the laser is. There it is. Oldest over here going all the way to the present. Again, this is the Precambrian, right? We're broken up into 3 sections. We're going to be talking about Mesoproterozoic. So over here, that'll be our first phase. And then we're going to jump up. Our next part of the story is over here, and then here, and then present. Okay? You all have that structure in mind? Okay. So now we need to suspend what we understand about the Earth a bit to go back to 1.5 billion years ago. The continents weren't where they are today. What about the landscape? We are Precambrian. Did we have fish? Plants? Trees? Grass? It's a very different landscape at that time. And so keep that in mind. We were in a supercontinent. Most of you have heard of supercontinents like Pangaea. We're going way before that. Okay. And so in this one that would build up later into Rodinia, we are talking about the Columbia Nuna supercontinent. We won't go too much into that, but that would be, they do go over that a bit in this research paper here. So continents in a different location. Some of our sediments, they source from Siberia, so being a continent near us. Some of our North American landmass didn't include places like where I grew up, like California, wasn't scraped on yet. And so things are very different than what we see today. But what we can do is start to piece together, okay, well, what did Montana look like? We have to rely on the rocks that are exposed. And so this picture is here just to show you that Glacier National Park isn't the only place with these super old rocks. That the old rocks that we can start painting a picture about what this environment looked like are part of what we call the belt supergroup. And within those rocks, if we focus on Glacier National Park, where it's very well exposed and you can drive a road through those layers, you're going to see a lot of different kinds of rocks. What color of rocks have you seen as you have gone through the park? Yell them out. Blue, red, green, yellow, white, purple, gray, all of them, orange. Have you ever heard of working in the visitor center? I know some of you have. You might have people come up to you and say, where's the Rainbow Pebble Beach? Anybody heard that before? What are they talking about? Maybe AI. We actually have rainbow rocks that looks like that. They're usually, and if they pull up a picture, it's Lake McDonald. And they're seeing, sometimes the colors are a little amped up. But that's generally what they're at. Where can I see this? The cool thing is you can see it throughout most of the park because those rocks are going to be throughout a lot of the park. You're going to see those rainbow color rocks. Now, the deposition of these, I put into that silt phase. And we're going back to about 1.5 billion years ago. We have this environment that's building up sediment. I want you to think about a landscape that is void of trees and plants. And what happens to sediment movement if you are in that kind of environment? You have wind, water. We're moving that stuff like gangbusters because what happens with erosion in plants? What do they do to erosion? Can anchor that sediment, hold it back, slow it down. Think of a time when we don't have that. We're gangbuster sediment moving through. So we move the sediment into somewhere it's going to deposit, like a basin, a water body, something in that. So we can look at the rocks to tell us a little bit more about what that environment might have looked like. Now, the red and green rocks, a lot of the rocks we have that look like this, we can get a better idea of what they're telling us by grinding them together a little bit. So if I take this rock, maybe I can release some grains. What do you see here? Can you see that? All right. This is a sedimentary rock, but it's been under a lot of pressure. It's been under so much pressure, it really holds together well. So I'm going to introduce you, there's another category, which you think of, it's called a metasedimentary. Pretty cool. This is a super tough rock. We have a lot of the green and the red, and we call them argillites. So everybody say it with me like you're a pirate. Argillite. What is it? What is it? Argillite. It's red and green mudstone made up of sediments. Now, I called this whole category silt. What is silt? You think of dirt. What else do you think of when you hear silt?
Erosion.
Erosion. Clay, sand. Fine, dusty. Okay, what do you think of when I say sand? Like silica. How many of you seen sand in your life? Kind of like this. What colors of sand have you seen? Black. Were you in Hawaii? Yeah. Green. Pink. White. Tan. It's kind of brown. Gray, all colors, because sand is a size. We're talking about sedimentary grains. Sand is a size. So it can be anything. There's really cool sand that's made up of tiny, tiny little shells, tiny fossils, tiny bits of plastic, modern day sand, tiny pieces of crab poop, like pilloidal sand. So there's all kinds of sand. Sand is a size when we're talking about sedimentary grains. And so the next size category down, we can go to finer than sand, silt and clay-sized particles. And so when I grind this rock, what do we call this? Super compacted mudstone? What do you call, what's the word? Argillite. Argillite. So argillite, when I grind it and I feel it, how would you describe it? Go ahead and feel this.
Powdery. Yeah.
Like powdery?
Yes.
Does it remind you of anything?
Soft.
Soft? Anybody change a diaper?
No, talcum powder.
Talcum powder, it's kind of that grain I want you to think of. The other thing, it's like cornstarch. Some can be a little more gritty if you have some bigger sized particles in there if you're in the park. So if you go down to the lake, grab 2 rocks, grab a red and green, grind them together and see what it feels like if it's more of a talcum powder or maybe a little gritty. But that's silt. And the cool thing about silt is it really beautifies what we see. And we'll get to that. I want you to think about how can silt make things even more beautiful in Glacier National Park. One thing I often do is you can really see it if you wipe it on your pants or shirt. Very fine grain sediment. So the silt, we have a lot of this making up our argillite, a lot of red and green rocks. And within that, we also see structures, sedimentary structures on the surface of some of the rocks. Can anybody see this? Yeah. Have you ever seen this in Glacier National Park? What is this? Ripples. Where have you seen ripples in modern day? Lakes, oceans, streams, rivers, creeks. Anybody ever seen a ripple on sand? Where? The desert, like on a dune, or at the beach? Yeah, so you can have water lane and wind-blown ripples. If you want to get really nerdy, there's a little index called the ripple index that you can measure the morphology of that ripple and figure out if it was more likely wind-blown or water lane. So I'll save you the nerdiness. I think this was water. So that helps us kind of think of the environment a little bit. But one thing alone, especially a sedimentary structure, you don't want to just rely on one thing to really paint that picture. Let's get some more evidence. And like I said, if I could have a fossil, that would be the best. It would really tell me a lot about this environment. This is one thing that we can, using some of the structures we've talked about, some have recreated what they imagined this environment looked like. Blakey does paleo reconstructions, and here's one. Can you find Montana? Right here. So glaciers up here in northwest Montana, and you'll see there's this water body. Now in the academic research, there's a hot debate. Was it a giant lake? Was it an open area that opened out to the marine environment? So there's 2 major camps that argue for either. But one thing we know, if we look, we can zoom in over here, we can look at some of our rocks and try to figure out a little bit more. It could have been either, but how deep was the water? What did it look like? We'll look through that. So this is the paper that I brought, Lawn et al. And this was one that they did in a special publication, just an overview of the Mesoproterozoic belt supergroup. So the rocks that I'm talking about from our silt phase. And what I wanted to point out, again, the massive volumes of sediment-laden water and its saline seas, so this one's arguing for that saline, maybe marine environment, were of enormous extent, but mostly very shallow and muddy. The sedimentary succession, so that stack of rocks that resulted, is the thickest on Earth. Although much progress has been made in understanding the alien landscape that was the Belt Basin, so think of that water body, many questions remain and await resolution by those geologists seeking a lifetime of challenging work. So deep time, those really wanting to get into the Precambrian. But think of this as the thickest succession of these aged rocks that we have. And one of the rocks that we have can help confirm some of that, especially that shallow part. Anybody see something like this before in the park? Okay. I like to think of it now, depending on the angle that you're looking at it, it's going to look different. Also, the colors will be different. In this case, I'm seeing red and green concentric layers that almost look like a target, the bullseye. It reminds me of a cabbage head that if you cut it in half and looked in, it would look like that concentric circle. Now, if it's on the side and it's cut in half, broken that way, you'll see that it's these rounded layers. Now, this can have a lot of different morphologies. It can be one mound, it could be connected mounds. This one also, pink and green. I often see ones like this as you're heading up. Anybody hiked the High Line before? High Line Trail. When you get up to the overlook portion, the Glacier Overlook Spur, there's some of these that you'll see. And as you're driving up the Going to the Sun Road, headed towards the loop, what's the loop? That hairpin turn on your way up to Logan Pass. Before you get to the first tunnel, we call it the West Tunnel, if you look on the right, you'll see something that has been described by others as looking like Van Gogh's Starry Night. This stack of swirling and layered kind of mounds. Anybody know what these are? Stromatolites. This is ancient cyanobacteria. This is our fossil that's going to help us understand a little bit more about this environment. Now, it can be red and green. You'll see those. You'll see some more red ones. You'll see gray ones. Here's one that is gray, and it looks more ruffled on the top, kind of crenulated, and it's smaller. There are some over by Grinnell Glacier as you get up towards the glacier that are big enough that I can sit in it, and that mound is around me. These are ancient colonies of cyanobacteria that would grow in mounds, and the environment around it would impact how it grew. That's one factor. And so sediments could coat it, and then new layers form on top. It can also force precipitation in the water, and it creates its own layers. So whatever it is, we're getting these layers and layers of layers. And the cyanobacteria are helping to pave the way for life to explode on Earth the way we know it. Because what do we need the most? Oxygen. We need oxygen. Where did the oxygen come from before plants and trees? Some volcanic outgassing. Something like cyanobacteria that did a process that rhymes with photosynthesis. Photosynthesis. Now, to do photosynthesis, these mounds of cyanobacteria, slimy mats, needed to be able to get the sun, right? So it takes in sunlight, and what is it producing as a byproduct? Oxygen through that photosynthesis process. So we know it needed to be in the photic zone, so not too deep in the water. And we can go to places today where you can see these organisms. Where on Earth do we see stromatolites today? Australia, Shark Bay, Australia, the Hamlin Pools would be one. And this is what I imagine when I see stromatolites in the park. There's this shallow water body, and it probably was like this. You have these mounds of cyanobacteria, not too deep water, and they're able to be producing that oxygen. And these guys have been throughout Earth's history. Their stromatolites were on Earth before the age of rocks we're even talking about. And so this is what I think of when I think of the silt times of Glacier National Park. We have gangbuster sediment moving, able to deposit in this water called the Belt Sea. Again, giant lake, giant sea, open to marine environment, questionable. But we know we had water, and we know we had stromatolites, and we know we deposited a lot of sediment. And over that time, that sediment compacted and became the layers that we see in the park. So the next part of the story is we need to get these layers up to the surface and saved from being doomed to metamorphose or melt and become igneous. So we're going to tilt and slide. So we silt and we tilt and slide. And we're going to get into plate tectonics. So as you know, the Earth is made up of, on the surface, plates. Those plates slam into each other. And depending on what the plates are made up of, you're going to see different landforms or different situations taking place. You've got the blue stuff, which is made up of a certain kind of crust. It's in the ocean. So what would we call that? What is it? What do you think? If you were going to guess. Oceanic crust. The green stuff is on the continents. What do we call that crust? Continental, A+. Love geology. So we have oceanic and continental, and they're made up of generally different densities. They're moving around like at the rate your nails grow, and as they slam into each other, they're going to do different things, create different formations and situations. So in this case, around 150 million years ago, I want us to think about what's happening now. We are way past 1.5 billion years ago. Lots of stuff happened in between, but this is the next phase of the story that we can see. So we have North America, and there is a plate slamming into the western edge. Okay, we have the Pacific plate. Now, if we had continent slamming into continent, we can make a mountain range. Think of India slamming into, making what? The Himalayas. If we have oceanic crust slamming into oceanic crust, we can create a trench. Anybody know where there's a trench today? Pacific Trench? Yeah. So we've got, those are the two situations. Now, what happens, they're doing different things. They have different densities. And let's oversimplify it. Let's think of the continental crust being light and fluffy, and the oceanic crust being thin and dense. So what happens when you slam the continental crust or with oceanic crust? From that pressure, maybe uplift. You can test it at your house because it's what I think, just like a piece of Texas toast. Have you ever had Texas toast? That fat slice of white bread? And think of a Pop-Tart. You ever had a Pop-Tart? Thin, dense, sugary Pop-Tart and a slice of white bread. Okay, what's this one representing? Continental crust. Oceanic crust, you're with me, right? Yeah. So now you put that on the kitchen table, you slam them together, and what do we get? We just built a mountain range a little bit. It also subducted. Is that cool? That pressure from the subduction is popping up mountains. And what we are is way out here in Montana, way away from that convergence area, and we're feeling that pressure. As the bread's popping up, we're starting to tilt. So I want everybody to put your hands up. Like, let's say you're holding hiking poles. And over time, we talked about silt. Remember, we laid down that huge stack of rocks. That stack of rocks from 1.5 billion years ago is going to be your pinkies. You're going to put your pinkies up. And then there's rocks that laid on top of that we don't see. And then we get to the time when the dinosaurs were here. Think of, okay, where's the oldest rocks in your stack?
Bottom.
Okay, where's the youngest? Okay, now, plate tectonics. We're feeling this pressure that Pop-Tart's shoving in, and we start to tilt. So everybody tilt, 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 tilt. Have you ever been under pressure for a long time? What happens? What are your choices? Maybe you were in a PhD program and you ran out of funding. Your advisor was MIA. What did you do? You snapped. All right. Not from, yes, personal experience, but you snap. That pressure didn't go away. It kept going, but we slid over on a fault. And over time, the rocks on the top were eroding away, and we leave that massive stack of Precambrian rocks sitting on top of dinosaur age rocks. That's how we got Glacier National Park rocks on top. Okay? Wasn't flipped, it slid, snapped, and slid over. So think of this, we get the Rockies forming, and pressure, snap, slide, Lewis overthrust. An overthrust talks about the angle. It's fairly shallow angle, and it's thrusting over. And you can see an exposure of it. I want you to think of Glacier National Park. It's actually shaped, if you include Waterton Glacier National Park, we're an international peace park with Waterton in Canada. So this would be like Waterton up here. Here's Glacier. Our rocks came from over here, popped up, slid over. So that thrust is underneath the park. And if you drive around to the tip down here near Summit or Marias Pass, you will see that side view where the line is exposed. You can see the thrust. And the other cool thing is that our rocks, what do we call, remember those argillites? Like a pirate? Super compacted mudstones. They make pretty good cliffs, which will lend itself to being beautifully carved by glaciers, but makes cliffs. Now underneath the Cretaceous, similar rocks, but they weren't under pressure for as long. They're not like our super compacted mudstones. They make more slopes. So as you're driving on Route 2 and you see that break and slope on the mountainside, where it goes slopey cliff, that's that fault zone right in between. And so find the obelisk. Anybody been here?
Yep.
Pull over. Now look across the street. Can you see the line? That's the exposure of the Lewis overthrust. Okay, so this thrust event happened over time, but around, I like to say, like Cretaceous dinosaur times, towards T-Rex times. It's around 65, 70 million years ago. That's the age of the rocks below, age of the rocks above, 1.5-ish billion years ago. So time's not working. If you hike up there, it's really cool. There's not really a trail, but you can get there. All right. And then over time, after the thrust, after that slid over, we later then shaped the park into what we see today. And the furthest edge of that thrust sheet is Chief Mountain. So if you've ever wondered, as you drive from the east to the park, where you're rolling, abrupt glacier, it's because that's the edge of the thrust sheet. And over time, we've eroded it and we shaped it. And we can see that, and the thrust goes beneath here. So the next final stage is we need to glide. We need to glaciate this place. This is Lyman B. Sperry with a crew who were charged by the Great Northern Railway. They were hired to find a trail to a glacier good enough for horses and women. And they tried several attempts. Lyman B. Sperry, who is a self-made naturalist, his nephew came along with him and wrote a little memoir. It's one of these rare books. It's not very well published, but it's funny. It's good to read. It gives you some insight of what it was like in the 1890s as they were here trying to find that route, because people could go to other areas and they had special features to show off. We wanted to tout this area. So the railroad was like, okay, let's get people to see glaciers. So he tried multiple times on Avalanche area, in the Avalanche Basin, to get a trail up to the glacier right above it. What do we call that glacier that's above Avalanche Lake? Sperry Glacier. Funny name. It's Lyman B. Sperry. They tried. They did not succeed. They couldn't find a route that would work, so they moved up a basin or moved to the next basin over, which is on what trail that goes outside of Lake McDonald Lodge. The Sperry Trail goes to the Sperry Chalet, and there's a great hike up to Sperry Glacier. And so they did get their trail, but really interesting. But most people, when they see white in the park and they're like, oh, is that a glacier? What's the answer? No, it's probably snowpack that you're seeing. Now, when George Bird Grinnell came to this area and he saw Glacier National Park, it's like, oh, he kind of had an idea that things were going to change quickly. And he was one of the proponents to try to establish Glacier National Park. In what year did it become a park? 1910. We became a national park. And the other cool thing happening at the same time is that while people were exploring this area, like Grinnell and Sperry, photography is really getting developed. So we have some pretty awesome records to see how things have changed over time. Like this glacier, which is Boulder Glacier. And I want you to keep those people in scale, think of them as scale, and then keep this peak in mind. Let's jump forward. This is from, we're gonna jump forward to the 80s and see what this looked like then. So what's the story? Changing. Things are changing. We're seeing that change. And those are our glaciers that we have. Today we have 26 active named glaciers. And to be considered a glacier, let's simplify it. We're gonna need 3 things to classify you as a glacier. One is it has to move. It needs to move under its own weight. And so it moves kind of like silly putty. Have you ever had silly putty stuck in your carpet? Maybe. Sometimes it gets loose in my backpack. That's not great. So, but silly putty's cool because it can move in different ways. What happens if I pull it slowly? It can flow, right? But what happens if I'm really, really strong and I pull it fast? What did I get? A really clean cut. It snapped. Glaciers flow. And as they go over terrain and maybe move abruptly, what forms? Crevasses. So those would be indicators of movement. Other indicators of movement in a glacier could be the stripes that we see in them, in big modern day ones like in Alaska. What is that stuff? Sediment that it's dragging along with it. And as other glaciers join in, you start getting more bands of that sediment being dragged in. So we can see those. But those crevasses would be one area that we know it's moving. And even if we're sitting there watching and like, I don't know if it's moving, that would be a good indicator. The other thing that we want is it to be forming glacial ice. And glacial ice isn't fridge ice. It's not a snowball. It is ice that is so compacted, it is so driven tight that the air is sealed off. We have air bubbles from the past in those ice cores. So glacial ice is super compacted snow. So you need some depth to be able to crush that into glacial ice. So we need to move. We need to be making glacial ice. And then in the park in general, we're looking at about a football field, about 25 acres in size, 25 football fields would be what you pretty much get. If you're that big, you're going to be probably moving under your own weight and making glacial ice. The other cool thing about glaciers is they're a pretty simple system. You have one half up here where accumulation is happening, and then you have an equilibrium line, and then areas below is where ice is melting out. And it's like a conveyor belt through that body. So even though a glacier can be sitting there and you're like, it hasn't moved, it's looked like that since I was 5. I remember seeing that as a child. It still looks the same. But what you're seeing is this balance between things coming in and things melting out, always moving through, kind of like a conveyor belt. Very similar to one of these guys. Anybody remember these? A checkbook? Is it easier to build up your savings account or spend it? Could be different for everyone. For me, it's really easy to spend. So that's kind of like glacial ice. It takes a lot longer to build glacial ice than to melt. So one great winter may not build back what we melted in a super hot summer. So we need continuous cold conditions so we can build that glacial ice up. Now we get great winters. Anybody recognize this building? This is Logan Pass. This is the visitor center at Logan Pass, and we have, this is the going to the Sun Road. See it back here? It would be coming up the hill, coming in, here's the parking lot. This was from 2011. We had a really good winter that year. And anybody guess what month this is? March, January? I believe this was May. No, it may have been, no, I think it was May because we start plowing in April. When we got up to the pass, this is what the snow looked like. This was in July. And I remember as an interpreter standing up there talking to people about glaciers, and week after week, because we would have one shift up there a week, that snowpack, what happened to it? Would drop about a foot every week. It didn't take long until it was like that. So we get a lot of snow, we melt a lot of snow. So we're seeing that continue. Anybody remember her? Lucy. This is Lucy. She was working at the chocolate factory and shenanigans happened. But as Lucy was charged to not drop a single truffle or lose any, she had to keep up on that and wrap each one. It started getting faster and faster. And when I see this, it makes me think of climate, our climate. And the Earth's, our geology story is a story of climate change. We, way back 1.5 billion years ago, was very different than what we see today. And those glaciers, as they melt, they're telling a story as well. And so if this was a glacier, the truffles coming out, that line of truffles coming out was a glacier, and Lucy is the climate, which is an average of weather over time. If she's able to keep up with that growth of the glacier, then that line, how big that glacier is going to stay the same, right? Now, what happens to if she's faster, she's eating that ice quicker than it's coming out? What happens to that glacier? It's receding, it's shrinking, but it's always moving forward. Does that make sense? And then same thing, if she slows down, it's cold enough where we're building. It's always moving forward and it's growing. So what we're seeing today is that the glacier's melting, but also moving. That can be a hard one to think about. But as they move, they shape and they sculpt the environment around them. And so I'm going to point out a few common things you're going to see, because this is telling me, if rocks could talk, this is telling me all about glaciation. Glaciers were here and they left their mark. So around the Pleistocene, 2.6 million years ago, now we're going to our glide. 2.6 million years ago, North America had two major ice sheets coming together near the Rockies, and glaciers in the mountains of the Rockies here in this area were going out towards those major ice sheets. But those glaciers were mountain glaciers, valley glaciers, and they leave behind certain shapes. So when you're at Logan Pass, I want you to think about this. This is what I see, that probably during the peak of this ice age, we had a sea of white with churning, moving glaciers carving underneath. And as they carve and freeze and refreeze to rocks beneath, they pluck and they leave behind certain shapes. So if you have one glacier on a hillside, so everybody put your hand up. Imagine there's a glacier, put your other hand there. And that glacier is, remember, moving like a conveyor belt. As it's carving rock, it's carrying out, spitting it out, and leaving behind, as you carve, that armchair-looking basin that we call what? A cirque. Circular basin, a cirque. One glacier would carve a cirque. Okay, really good example of a cirque. Here's me as an intern in 2008. This little baby Tegan. So excited to be at Avalanche Lake, where you have a little lake, and if I spit in my hand, there's Avalanche Lake sitting in a cirque basin carved out by one glacier. Now, what happens if you have glacier on one side of a mountain and a glacier on the other side? So put your hands together. It's a nice little stretch. And those are carving. We get this fin of a ridge left behind. What would we call that? An arête. So this is one of my favorite views. This is what I think of when I'm driving up, going to the Sun Road, just about to get to Logan Pass to grab that last parking spot. And I see a mountain. This is what I'm seeing the past. The glacier's right there. As a glacier carves, rivers carve valleys that are shaped like what? A V. If you shove a glacier through there, you'll leave behind what shape? A U. So underneath this glacier on this side, you have a U. And then sometimes there's a glacier nearby that's not as deep. So it's not digging as deep of a U. It might hang up higher. You have maybe a shallower U here. And as they're coming together, that debris that they're shaving off comes together into moraine to later be dumped off. And then if I melt away, that's what I see. Can you see the glaciers? We would have had one here joining with this one. This is where there's a waterfall, Birdwoman Falls. Shallower glacier, deeper, joining together, coalescing, and going into the McDonald Major Glacier. Another arête that we have, so I didn't point out the arête. So in between them, here's your knife edge ridge. And what about here? The Garden Wall. So at some point along that wall, you had glaciers either side by side, back to back. One could have been moving this way. Whatever movement it's doing, you have two eating away at that area to leave behind a knife edge ridge. Now, what if you have 3 or more glaciers? What shape do you leave behind? So someone make me a cirque. Yeah. Hold it up real high. Okay. What shape, if I have 3 or more, are we getting? A pyramidal peak, most famous in Disneyland, is the Matterhorn, right? Or the Swiss and Italian Alps, which translates to the horn coming out of the meadow. You have that beautiful pyramidal peak. We have several of those in the park. Really good example. Anybody know this little peak? You can see it from the foot of Lake McDonald. Not Edwards. Look at this one. Not Mount Brown. The little Matterhorn. So cute. We have our own Matterhorn. Underneath it is what lake? This is from Snyder Lake off the Sperry Trail. You could go up a different way and get to Snyder, and on the other side, Avalanche Basin. So we have the little Matterhorn. We also have Mount Reynolds, another great horn. So U versus V, we already talked about it. What carves a U? V? Rivers. So here's rivers. Maybe this is what the environment looked like before the Ice Age. Shove some glaciers in and we start getting all those shapes. So one glacier, what's the shape left behind? Tube. Arête. 3 or more? A horn. Excellent. And I love this. How many of you remember this? Anybody have one? I can't think of a better example, and I know it's getting outdated, but this is a glacier. This is a beautiful example of what glaciers do. Remember that question I asked in the beginning? How could silt make something beautiful? This. Pet Egg Glacier. So What a glacier does is as it's moving, it's shaving the rock underneath it, it's carving it, and it can make something called rock flour. And the glacier picks it up and moves it with it. As the glacier melts, that rock flour can go into a basin. This is to beautify your feet. It's a pet egg. You can shave the dead skin off your foot. It gathers those little pieces, and then you dump it out in a basin like a trash can. And that's what glaciers do. And that silt that was dumped out, glaciers as they carve, they leave behind these little lines that we call glacial striations. This might be a little hard if I hit the light right. Maybe you'll see some scratch marks as it's carving and shaving off tiny grains. You get the rock flour, dump it in the basin, and as light hits those little tiny silt grains, silt and clay-sized particles, it interacts and puts off what color? Blues, teals. And if you get to most of the water in the park, you're going to see it's carrying that sediment. And depending on the depth of the water, how close it is to an active glacier, the angle of the sunlight, it's going to look different colors. So here, like at a river, you can even see where the fastest moving water is because it's carrying the most sediment and it's more teal. As you get closer to the edge of the rivers, it's clear because we're depositing that sediment. It's not carrying it. So that sediment is interacting with the light, giving us the color. And in some cases, you get this rainbow of blues as you get further from the glacier. So anybody know this valley? This is Swift Current Valley. Or no, you're right, it's the Grinnell. So as we Grinnell here from the glacier overlook above Highline, as we look down, this is the most teal. When this is fairly iced over at this point, but during the summer, especially as you get to August, the water is exposed. It's very teal, kind of like your shirts and jackets. And then as you get to the next lake down, it gets a little bit less teal and then cobalt blue as you get further away, because that sediment is kind of winnowing out. We're depositing it. We're carrying it from that active glacier down. So thank you, active glaciers and that sediment, for making these incredibly beautiful waterways in the park. And so all of this story that we've talked about, we can hang on 4 parts of a structure. Our 4 key words. What's the first word? Silt. Second? Third? Fourth? So silt, I want you to think mud, bacteria. What's the name of the fossil? Stromatolite. And it does what? That rhymes with photosynthesis? All right, this is our time when we're building the layers that will later become what we see on the surface. We silt. And then we tilt. Why are we tilting? Pressure from what? Plate tectonics. And we're feeling that pressure, and our rocks down here, what happens? They snap and slide. They're eroding away, leaving the oldest on the top because of the Lewis thrust fault. So we slide, and then all those rocks that are Precambrian age, that were super compacted mudstones, a lot of them, we have limestones too, there's some igneous rocks in there. All of those get shaved and carved and eroded over time. And then major carvers make the shapes we see today, like during the Pleistocene Ice Age, 2.6 to around 12,000 years ago. And what shapes do we see? What valley shape do we see? U-shaped valleys. What about basins? One glacier carves out a 2, 3 or more horns. All those shapes are talking about that Pleistocene Ice Age glaciation. And then around 12,000 years ago, or 6,000 to 7,000 years ago, our little glaciers form to polish the surface, continue to put that silt out into the water, and give us the beautiful colors we see throughout the park. And so all of this, we silt, tilt, slide, and glide. And to really bring it home, I'm going to make you sing a song. All right. Have you ever heard of Row, Row, Row Your Boat? I'll mimic it for you first, and then we'll do it together. So it'll go silt, tilt, slide, and glide. That's how Glacier formed, Glacier National Park. Mud, bacteria, mountains, and glaciers. cirques, arrettes, and horns. So if I can sing off key, so can you. So are you ready to join me? Silt, tilt, slide, and glide, that's how glacier forms. Mud, bacteria, mountains, and glaciers, cirques, arrettes, and horns. And that's the geologic history of Glacier National Park. So thank you.
Wow. Awesome. Thank you.
Yeah, if you need my business card, feel free to email. I have other resources I can send you. And then I have these significance cards where the park head summarized some of the 5 significant reasons we are Glacier National Park, a national park. And 2 of them you tie right back to the geology. So if you want to pick up these, it also has part of the Organic Act, which is always good to remember on the back. Yeah.
Okay, raise your hand and I'll bring the mic to you so everybody can hear your question. Who has questions? We're here.
I'm familiar with Argillite. There's, you familiar with the Argillite in the Haida Gwaii area? It's black Argillite. It's used in the art there.
Oh,
Black is coal.
yeah.
And it's carved. It's extremely expensive.
Yeah, that's awesome.
So
Do you know, is it because of like, do you know what age it is?
Nothing about it. Except they call it Argillite.
Yeah.
It's, you know, a piece this big is 4,000.
Oh, geez. It's probably
carved,
rare.
Carved.
Yeah. Interesting. I'll have to look it up.
They quarry it by hand.
Yeah.
Chisels.
What area is that?
Haida Gwaii, Queen Charlotte Islands off British Columbia.
Okay.
It's the westernmost part of Canada.
Yeah.
It's on
Accessible
the
only by
extreme
the
west.
Tlingit and Haida people.
Wow.
They don't let anyone else.
So who's selling it? I have so many questions.
As art.
Yeah. Interesting.
And the quarry is secret.
Mhm.
You can't go there.
Yeah. Well, email me sometime.
I have a whole book on it.
Yeah, that'd be really interesting to
Yeah, I have
see.
a whole book just on that.
Yeah.
I'll bring it over to you.
Yeah. I'm at headquarters at Glacier National Park in West Glacier.
Any other questions?
Are there any rock climbers in here? Are there any first ascensionists in Glacier? So Tegan, my question is, why is Glacier so challenging to climb?
Yeah, I think that there could be some different things. Are you talking about like management wise or because of the rocks?
Specifically because of the rocks.
Yes. I think it goes back to they're not great rocks to climb. What kind of rocks do you prefer to climb on? Limestone. What else? Granite, maybe sandstone. Yeah, they're just not. While they make good cliffs and like the layers that we have, they're really, there's extensive layers. They do vary. They are fractured, and I think it's just not great for bolting. So you're not going to see a lot of climbers here like you would at Yosemite. It's not the right type of rocks. But there's a lot of really good opportunities for rock scrambling and doing like peak bagging, those kind of things. Yeah.
The best rock is St. Nicholas. That's the least crumbly.
Yeah. Perfect.
Another question back here.
So up at Pekin Pass,
Yeah.
there's some really beautiful, interesting rock that's kind of a light yellow with cobalt blue veining. It's like off to the right.
Yeah.
And it almost feels like shale when you're walking on it.
Yeah.
I was curious what it's called and the age of that rock, if you're familiar with that area.
It's going to be the same age as the Precambrian rocks. They're all part of that, so everything in that area. I'm thinking what you're seeing is more of probably more altered part of that argillite or things that are pretty much almost to slate. And that's why, is it really clinky when you walk on it? Yeah. Yeah, you'll see differences as you're walking on materials in the park where some sound less clinky and others more. I think that's more altered. Maybe it was had a different, I don't know if it was chemical or pressure, but whatever it is, it's definitely closer to what I would consider like a slate. But it's still, I would think it could be the argillite still, just more altered. But yeah, yes. Oh,
You'd said that the edge of the park where it meets the plains is kind of thrust event. How far south does that extend?
yeah. So the Bob, it does go south of the park. Now the Bob, you're getting into younger rocks. Like, were there fossils in the Bob? Has anybody ever seen them? Trilobites is much younger than what we're seeing in the park. So it's I don't have it off the top of my head how far it extends, but it doesn't go all the way. You're going to see different fractures and different rocks exposed, which give you different ages of units exposed. So you're going to get more stories that we don't see in Glacier National Park because those ages are exposed where they aren't in the park. Yeah, but it does extend beyond Glacier a little bit.
Yeah, so I graduated U of M in '90, and one of my professors was Dr. Don Winston.
Yeah.
His theory is that this edge here in the Swans was the eastern edge of a opening continental spreading.
Like a
unit,
rift, yeah.
A rift.
Mhm.
And it created, the back arc basins and all that stuff. And his theory is that everything between here and the Flathead Valley and
Yeah.
the current coast is an accreted terrain.
Yeah.
So what do you think of that?
I think that sounds great. Yeah, it's scraped on over time. Yeah.
And that explains we're at the southern end of the Rocky Mountain Trench.
Yeah.
So that also explains it.
Yeah. I would say anyone else who's like, oh yeah, talk more about that. Grab one of these papers I brought. That goes into some of this ideas. They compare the different ideas, including Winston's ideas, and yeah, very very fascinating. And that was one idea for how this basin formed, the Belt Sea, was that it was a rift basin.
Well, particularly when you said that some of the sediment comes from Siberia. I mean, his idea is that the other side of that rift now resides in Western Mongolia.
Yeah.
Siberian plateau.
Yeah. And you'll see some rocks like we have now. One rock I didn't talk about is the molar tooth structure. A lot of stuff built in the park, like the infrastructure bridges, for example. You'll see this weird gray rock that looks like lasagna that you dragged a stick through. Probably the best example is the saddle right before you get to Haystack Butte, or that area right before the saddle as you're hiking the Highline Trail. There's really nice units of it where it looks like lasagna. It's all messed up. And that's molar tooth structure. Really cool rock. We can talk about it sometime. But it's one of those rocks where the present isn't the key to the past because we don't have a modern day equivalent forming today. So some weird conditions happening back in the Precambrian that formed those. And yeah, part of this, there's a lot of interesting things we could go into. But not always. You can't pigeonhole Mother Nature. Yeah.
One more over here. Can you talk about the diorite sill?
Yeah, that's the other one I didn't talk about. And as she was talking about, rifting, and towards the end of the basin of the Belt Sea, after the rocks had already been buried, we have some igneous events or some volcanic events that are we have evidence of in the park on top of and within the rock units. So the rocks were already there. And then we had magma. Now think of molten rock. If it's below ground, what do we call it? Magma. If it's above ground, lava. That's intrusive versus extrusive. It depends on if you're above the surface or below. And then if it cools slowly, you can start identifying different things by the shapes, what it looks like, what it's made up of. In our case, we have both kinds. We have some that came above surface and some that cooled within the rock layers, but they were different times and different events. So the sills, like you see in many glacier, it's a big, looks like a black band with white on both sides. And there's other sills in the park too. The rocks were already there. That intruded up, was trying to get to the surface, find pressure, that pressurized molten rock, found a weakness plane within the rock units, squirt out, making kind of like a plane, cooled, baked the rock above and below, making it metamorphosed through heat, contact metamorphism. What a lot of times you're seeing is limestone. What happens when you metamorphose limestone? Marble. So we have a low-grade marble band now that was baked just by the heat of that intrusion. So we have sills, and then at a different time, younger than that, in other areas of the park, we had lava, because of this rifting activity that's happening, came up onto the surface when the rocks were still forming. So it's it's in the Belt Sea time towards the end. We see lava flows. So if you've been to Boulder Pass, you can walk on those lava flows. If you've ever camped up at Boulder, it's like a different park because you're seeing a lot of that igneous rock, the extrusive kind of tongue of lava flows that happen, the Pahoehoe flows. But yeah, we do have a lot of sills in the park, different phase, but think the sills formed after the rocks had already, sediments had become rock.
Do we have time for one more?
Yes.
So what type of igneous rock are those, the igneous rock at Boulder? And also, is that the same rock that's at Granite or Chalet?
Yeah, so I wish I brought a geologic map. We do have a digital geologic map that you can find if you Google the National Park Service. If you just do geology, there's a geological resources division, and they have a page on Glacier and links to the digital geologic map. And you can see where the igneous rocks are. Those lava flows, there's some that are exposed on Flat Top and some that are up in Boulder. So that's the purple on the map. And then with the sills, those are throughout the park in different areas. We have dikes, which are vertical, sills, which are horizontal. So you'll see some of those. And then your question was what kind of rock? The extrusive rock we also have pillow basalts. So if that lava flow that extruded to the surface flowed into water, like the Belt Sea, it quenched it, cooled it really fast, and you get pillow basalt. So that's what the extrusive rocks are, is basalt. And then the intrusive rocks are going to be there. It varies because it's mixed different minerals throughout, but you'll hear it called diorite, a gabbro-diorite, or dioritic sill. That's the kind of stuff. So sometimes it looks real salt and peppery, like a diorite, and other times it's really a lot darker, more mafic. Yeah.
Thank you.
Favorite rock?
Yeah. Oh. How do you pick a favorite child? I think, let me think about it. There's something I didn't talk about it, but one thing I get really excited about is mud chip breccia. And basically it's like mud balls that are wrapped up in sand. So if there's some kind of major wave event that happened that was high energy and it dragged mud and rolled it in other sediments like sand, you get these little balls suspended in white, almost quartzite now. You'll see bands of it near Sperry Chalet. You see it if you walk along Avalanche Lake. I really like sedimentary structures, so that would probably be one of my favorites. Stromatolites are really cool too. I don't get tired of seeing those, but yeah.
Tegan, thank you very much.
Yeah, thank you.